Oh, welcome back. So we have learned the graphical solution technique, and we have also seen how we can easily analyze the gradient of the objective function about the point at the optimal solution, and tally that with the calculations done by solver in the sensitivity report. And so now everything seems to like come back in one piece. There's nothing magical about solver's ability to solve. It can solve faster and much more complex models with many variables and constraints. Fine, but the basic principle remains the same. And here at this point, we want to go back to one of the points I made earlier on about the assumption that in our simplistic model, there was only one optimal solution. So indeed, that was the case because I already knew that, and I picked this model because it's or constructed this model because it's easy to understand. Um, but what are the four possible scenarios? It's good to know because we definitely know that no matter how simple or complicated your LP model becomes, there are only four cases, four possible scenarios of optimal solutions. So let's look at them. Okay, scenario number one is the easiest and most familiar. Is what we have seen, right? There is one unique optimal solution. So this is unique. It is um, only one, and it occurs when, in most cases, and in most cases, as in if we just specify the constraints and not have redundant constraints, not have constraints that have special relationship with each other, as we'll see. So in one example that we have seen here, we constructed the constraints out of boss's requirements, so to speak, and they worked out well, right? And every additional constraint that we add simply results in cutting off one corner and replacing it with two corners, thereby adding a net addition of one corner. So therefore, if we have 100 constraints, we expect to have 100 corner points. So that was the case, and in most cases, that is the situation. But it's good to know to what extent can other cases appear. So another scenario is when you have no solution to be found. Okay, when there's no solution to be found, it is only because that the feasible region has been nullified, has been cut off so thin that no point exists anymore. So, for example, you might have a situation, as we saw just now. I won't draw it too large, not just because I'm running out of space, but it's not necessary to show the point. So we have the non-negativity uh, constraints, obviously. And then the boss says, we cannot manufacture more than that. And then the marketing department says, we cannot produce more than this number because we need to brand it properly. Then production department might say, you cannot do it so quickly. And then finance might say, we have a lot of budget left. We better spend some of the money. And then you have the board of directors coming in, hey, you need to be strategic about things. And then you have another human resource department saying that, you know what, manpower is tight, actually we cannot hire more than this number of people. And you get the idea. Yeah, so when there are too many constraints and people as in, due to situations or whatever, it need not be political or subjective, but policies, initiatives, requirements, general thoughts, business philosophy, etc., can come in to have contradicting demands. So if that happens, no way means no way, right? You cannot have more than this number of people, this number of hours of operations. But I want to conquer the world. I want to be market number one. I want to be the most voluminous supplier in the whole world. How can that logic, persist? So if that doesn't make sense, neither can mathematics, neither can solver. So sometimes we can list and list and list and keep adding more and more constraints. All right, you can keep adding, but that doesn't mean it will work out fine. So in the end, if actually there is no more feasible region because it has been rendered void because of all the intersecting, remember we are cutting off a piece of the remaining feasible region all the time as we add another constraints. So as you add more and more, it is logical to think that very likely your feasible region is going to be reduced. It will never be the case that when you add another constraint, your feasible region increases. At the most, it stays the same when you add that constraint. Why? Because it's redundant constraints. Saying it is as if you didn't say it. Right? Saying it is as if you didn't say it. So when you add an additional constraint and it doesn't cut the feasible region, number one, it's redundant. Number two, the feasible region doesn't expand, it stays the same. And in general, if you add a constraint, it tends to reduce the feasible region. So in the worst case, there is no solution. Okay. Now, in the third case, you will have an infinite number of solutions. Why? Well, that means you do have solution and you have infinitely many number of choices. So what that means is, for example, I'll just show you an example, and you can quickly understand why that's the case. So we again have requirements, okay, and they are reasonable. So non-negativity and so on, and you have don't produce more than this, don't produce more than that, and then you have this constraint. Okay, nice. Okay, but what if your objective function turns out to be a multiple, that means parallel, to one of the constraints that touches the optimal solution. So we kind of know that the optimal solution is here, right? I mean, I still have one corner, but that's not important here. So we know the optimal solution is here. What if the objective function is not 5x1 plus 2x2, but 3x1 plus 4x2? Then we'll draw an arbitrary number, which can be 36, and then you'll find that we'll actually move it, and eventually it will overlay on top of the constraint that touches the optimal solution. And in this case, because the entire line contains equally highest amount of profit, remember our discussion just now? Yeah. So the entire line contains the profit 10, right? So the entire line will contains the profit 46, and all points on the line will be equally good. And we not only have one point, we have a line segment. So the optimal solution will be this whole series of points in this line segment because they all intersect the feasible region and they are all equally good. If that is the case, then we will end up having, number one, infinite number of optimal solutions. Number two, all the optimal solutions, all infinite number of points here, all evaluate to the same amount of profit, finite profit, like $46 per week. Okay, so the total profit is not maximum, it's not infinity, but number of choices to make tables and chairs, that's a lot of them. And they have to satisfy this linear equation. Okay. And so how do we choose? Well, we have to introduce something that is subjective, like, well, I think I like to have less chair than table, something like that. So we'll pick um, less chair than table, so smaller x1 and a slightly larger x2. And that is not fair because we never stated that in the original model. No wonder you have infinite number of solutions. Okay, so this can arise sometimes because of lack of sufficient constraints. Yeah, so we didn't specify enough, so that's why we end up having the same. But more importantly, it also requires the objective function coefficients to be aligned or multiple of the of one of the constraint lines, right, that touch the optimal solution. So this can arise, for example, because the coefficient of x1 actually was $3.05, but somehow or other we round down to 3. The profit for chair was supposed to be $3.98, but we kind of round up to $4. So if that's the case, then you end up originally there's a slight tilt in the gradient of the objective function. I exaggerate here, right? But there's a slight tilt. In mathematics, even if there's a slight tilt, it will kind of converge to a single point, right? Because then the intersection is unique. Or it can be tilting this way, then we'll just conclude that the other point is the optimal solution, and then we are back to unique solution. But when you round the coefficients, accidentally, it becomes collinear with the boundary constraint line, then we'll have infinite number of solutions. Okay, so the way to resolve it is to check the precision, the number of decimal places of your objective function coefficient and the constraint coefficients. Check that they are accurate because your problem on hand is very sensitive, right? If they are accurate, like 3, 4 and 3, 4, right? 3, 4 for objective coefficients, 3, 4 for the constraint line. If they're accurate and there's no mistake, then we will have to accept the fact that there's infinite number of solutions, and then we pick and choose based on some subjective criteria.